All right, hi everyone. We are going to be solving an example from page 24. All right, so let's read the question and there's some important detail I want to talk about. So example, we have an electron moving through a uniform magnetic field of 0.5 Tesla. The field is directly parallel to the positive x-axis. What is the magnetic force on the electron when it is moving with a velocity v is equal to 2 in the x direction plus 4 in the y direction plus 0 in the z direction multiplied by 5,000 meters second? Show that we get the same result using the right-hand rule. So this last sentence is a bit weird. Basically, initially, I was solving this example using the cross product definition, and I noticed that I was losing nearly all my students. So let's simply go straight to solving that question using the right-hand rule. Now, let's have an idea of the force. So we are going to be drawing a force diagram over here, and obviously it's a 3D vector, so there is a z-axis coming out. All right. By the way, I don't think I mentioned this in some previous video, but the z-axis is all actually the cross product from the x and the y-axis. What do I mean by that? Well, if you point your finger toward the x-axis, curl your finger toward the y-axis, the finger is pointing the positive z-axis. So going out of the board and going into the board is the negative z-axis. Okay, so that's a convention. It is always like that. All right, so we need to draw our vector on the vector diagram. We're going to start with the magnetic field vector. Notice that this one is pointing strictly in the x direction. So we got our B vector over here. It's a 1D vector already. We got our velocity vector. This one is going twice more in the y direction than in the z direction, so we need to take that into consideration. We will eventually need to find the angle between these two vectors, and if you ever have to figure out the angle between two vectors like this, it will be more obvious. Generally, one of the two vectors is on the x and y direction. Okay, I don't think I will ever try to trick you here. Okay, there are some problems that are a bit more challenging though. All right, now if we want to know the direction of the force, we need to use the right-hand rule. We point our finger toward the velocity vector, curl our finger toward the magnetic field vector. In this case, it's not exactly 90 degrees between the two, but the same logic apply. And I got my thumb pointing into the board. However, the charge is an electron. It's a negative charge. So my thumb pointing in, the true direction is 180 degrees out of phase, so pointing out. So the force, Fm, is pointing out in this case. Okay, so that's important. And in this case, when we say it's pointing out, that means it's pointing in the z direction, okay? In the positive z direction. All right, so that's important. Now, we just found the direction of our vector. It's going to be in the, like I mentioned, the z direction. I'm actually going to write the value for the magnetic force right after, just to show something. So magnetic force vector, we know right away that the x direction, there won't be any component in the x direction for the force, the magnetic force, since it's purely a 1D vector in the positive z direction. So plus 0 in the y direction, and also plus on the z-axis. I don't know the magnitude yet, but I do know that it's pointing in the positive direction. So right away, just using the right-hand rule, we almost solve our problem. We just need to find the magnitude. Well, the magnitude is equal to QVB sine of the angle. Now note, to find the angle over here, we will use the inverse tangent of the opposite side of this angle divided by the edges inside of this angle, so 4 divided by 2. So if we input Q in this case is E. Now note, I'm not writing the minus. The minus E was only important for the direction of the vector. We already figured that part out, okay? So we need the value, E over here. The velocity, this we need to use Pythagorean theorem, so square root of 2 square plus 4 square multiplied by, we need to take into account the 5,000 also. So 5,000 square Okay, multiply by the magnetic field. Magnitude of the magnetic field is 0.5. Sine of the angle theta, and that will be the inverse tan of 4, 2 right here. Okay, so obviously I wrote everything on the same line just because it's easier to visualize that way, otherwise I will have to erase half the board. All right, once we input all these values, what we get for the magnitude is 10,000 multiplied by the electron charge. So that's our magnetic force vector. 0 in the x, 0 in the y, plus 10,000 multiplied by the electron charge in the positive z direction. All right, so it's not too complicated, but you do need to master each and every part. Just like we did in the beginning of this semester, we calculate, we figure out the direction of the vector, then the magnitude, and we combine both of them together. We could use advanced vector calculus to solve this, but I think it's more intuitive when we simply calculate the magnitude and looking at the diagram, we determine the direction, okay? In a case like this, we could right away use the cross product definition. But like I said, it's not possible in all situations, so it's better to just practice with the right hand rule because that's what you will need to solve the question in the test. All right, so we're done with this question. Let's move on to solve some more question.